So hello everyone. Today I'm going to present our work, uh, self-paced continual learning with adaptive curriculum and memory replay. And so the concept of the self-paced learning, which embeds the training curriculum design into the model learning, is first proposed in 2010 at NIPS. This incorporates a regularization term in the learning objective to adjust the difficulty of samples in the curriculum so that the model can learn progressively from easier to harder samples. Previous studies has demonstrated that a well-designed curriculum improves our generalization abilities, task performance, and conversion speed during training. Previous research finding has shown that the self-paced learning significantly influences model performance as demonstrated in this figure. The key factor here is the parameter P, which controls the balance between the simple and complex samples. When P is positive, it forces the model to learn progressively from simple to complex samples, resulting in enhanced performance. However, when P is negative, we observe performance degradation due to catastrophic forgetting, essentially, which is the loss of previously acquired knowledge. Moving on to the multitask learning application, self-paced learning has proven successful in improving the performance in multiple studies. This success is largely attributed to its effectiveness management of samples with varying difficulties. Now, this brings us to an interesting opportunity in continual learning. Despite sharing similar challenges with multiple task-based learning, particularly in managing tasks of varying difficulty, there is a surprisingly limited research exploring the self-paced learning in continual learning context. The few existing studies have only looked at the predefined task sequences. However, this approach has limited practical application because real-world continual learning scenarios typically involve the unpredictable task orders. Given these findings, we see a clear research gap, and there's a need to develop a new method that effectively incorporates self-paced learning concept into continual learning. Currently, artificial neural networks suffer from the catastrophic forgetting, where they forget previously learned information when learning new tasks sequentially. Various approaches, including regularization, replay, and architecture-based methods, have been proposed to address this issue. And we drew the inspiration from the human education, where students learn through adaptive curriculum and review past mistakes. This figure illustrates the adaptive curriculum and memory replay process in human education. In this process, students study simpler problems before progressing to more complex ones within each task, which is an adaptive curriculum process. After completing each task, students review their mistakes and create a mistake notebook for incorrect answers. And when moving on to the next task, the students revisit and reinforce their knowledge from the previous task, building on their foundation to tackle the increasingly more complex challenges, which is adaptive memory replay process. And our method sprint mirrors these two core principles of the human learning process, enabling continuous learning that respond to the model's current capabilities. Now, let me explain the detailed methodology of Sprint. To integrate the self-paced learning principles into continual learning, we developed two self-paced sampling methods that adapt the sample complexity for both new and previous tasks to the model's current learning capacity. In the former, the loss function is used to estimate the complexity of each new sample, while in latter, forgetting occurrences are measured during the training process to estimate the complexity of previously learned samples. First, self-paced sampling for new tasks selects the simple to more complex samples for each new task based on the current learning ability of the model. At each epoch, we select samples in the order governed by a loss function, which identifies easy samples based on the loss values that are less than a predefined threshold lambda. This threshold is gradually annealed over epochs, allowing us to learn harder samples as the iteration proceeds. As you can see in this equation, the loss function consists of three terms in sequence. First, a weighted loss of samples in the current task. Second, a regularization term on the weights of the samples in the current task. And third, an unweighted loss for samples in the replay memory. We train the model by alternately optimizing two variables, which are model parameter theta and the latent weight variable vi. Here, the regularization term vi is applied only to the samples in the current task datasets to prioritize in-memory samples from previous task. As outlined in this algorithm, the model parameter theta are updated by minimizing our self-paced loss function that distinguish between samples from the current task dataset, dt, and the replay memory m. Specifically, for each sample in I belonging to the dt, if the loss value is below the threshold lambda, the latent weight variable vi is set to 1, thus incorporating the full loss value into the model optimization. And conversely, if the loss exceeds lambda, the vi is set to 0, effectively excluding that sample from contributing to the current epoch's learning process. For the samples in the memory, the loss value is directly incorporated into the model update without the vi weighting. Second, self-paced sampling for previous tasks with memory replay records the forgetting occurrences for the samples in the previous task to determine which samples from previous tasks should be maintained in the memory. Inspired by the previous studies suggesting that the samples that experience the forgettings are more effective in improving the performance of the model compared to those that did not undergo forgetting when learning new tasks. We select the samples that have undergone forgetting for the current model as in-memory samples. Here, a sample is considered to have experienced a forgetting occurrence when it was correctly predicted in the previous epoch, but is incorrectly predicted in the current epoch. We found that this sampling for memory replay deals with simpler to more complex samples according to our self-paced learning principles. The below figure demonstrates the average number of forgetting occurrences for in-memory samples across 5 tasks on Cypher10 datasets. The result reveals a gradual increase in the average number of forgetting occurrences of in-memory samples as the new task accumulates in both disjoint and blurry 10 scenarios. This indicates that Sprint manages forgetting samples in the order of simpler to more complex. This intrinsic property of forgetting occurrences not only aligns with the principles of the self-paced learning, but also indicates it as an effective criterion for assessing the complexity of samples. And this algorithm shows how Sprint updates the replay memory at the end of each task, and we first exclude samples without forgetting occurrences. Then, we apply the reservoir sampling to the samples having forgetting occurrences to update the replay memory. This sampling strategy, which has proven effective in managing the replay memory in the scenarios where the null task identity is given at the inference time, maintains a fixed memory of size k and uniformly sample from the input data stream. The proposed dual self-paced sampling enables the model to enhance its ability to generalize the new task and retain the knowledge for previous tasks effectively in the continual learning scenarios. This final algorithm describes the sprint method across a sequence of tasks. For each task, we first merge current datasets with in-memory samples. Then we apply the data augmentation strategies to all data samples with a probability of tau% to enhance the generalization ability and robustness to the new task of sprint. Here, we employ the auto-augment and cut-mix data augmentation strategies, which are identical to those employed in Rainbow Memory, which are one of our comparison baselines. Auto-augment strategy randomly selects the parameters to determine the number of augmentation and their magnitudes. Cut-mix generates the new training samples by combining random regions from arbitrary chosen two images and their corresponding labels. Then, to learn a model and a curriculum from the merged datasets, we employ our self-paced loss function. Using the model's prediction during the training process, we compute whether the forgetting occurs or not. At the end of each epoch, the learning threshold lambda is adjusted by a scaling factor mu. Once training for the current task is complete, the algorithm updates the replay memory based on the measured forgetting occurrences. We evaluate our sprint on class incremental task using the Cypher10, Cypher100, and ImageNet100 datasets. For each dataset, we randomly divide the total number of classes into the multiple tasks. Specifically, we split the Cypher10 into the 5 tasks with 2 classes per task, and Cypher10 and ImageNet10, Cypher100 and ImageNet100 into the 5 tasks with 20 classes per task. We evaluate the sprint and its comparison on 2 different class incremental scenarios. The first scenario is the disjoint scenario, which is the traditional class incremental setting, and the second one is the blurry scenario, where each task consists of a mixture of samples from its assigned major and minor classes from other tasks. In our blurry 10 scenario means that 90% of the samples are from the major classes and the 10% are from the minor classes. The example of this blurry 10 setup is shown in the below figure. And we use the following metrics to evaluate the performance of continual learning models. Last accuracy, which is the model's final performance after learning all tasks, and average accuracy, is the average of accuracies throughout all tasks. And the last forgetting metric is average maximum forgetting of all tasks, which is the drop in the performance of each task at the end of training compared to peak performance. For the comparisons, we utilize the following 8 continual learning baseline methods. All methods utilize ResNet 10, ResNet 18, ResNet 32, and ResNet 34 as their network architecture for Cypher10, Cypher100, and ImageNet100 respectively. This table compares the last accuracy and average accuracy between the sprint and the other comparison method across various scenarios and datasets. The table denotes the top 3 methodologies, with the best performing method highlighted in bold, the second best method with the solid line, and the third method with a dashed line. These results demonstrate that in every blurry 10 setting, sprint outperforms all other comparison methods in terms of last accuracy. Sprint exhibits remarkable consistency, being the only method to rank within the top 2 across all cases, and its average of 1.33 is the highest among all comparisons, significantly surpassing the next best method, Rainbow Memory, which has average rank of 2.42. In this page, the table compares the performance in the Cypher10 Blurry 10 setup for 3 different memory sizes. The result demonstrates that Sprint consistently outperforms all other comparison methods in terms of both performance metric. As memory size decreases, the performance gap between the Sprint and the average of other baseline method widens. This result demonstrates the effectiveness of in-memory sampling in Sprint even when the memory size is limited. This table shows the effects of data augmentation on performance by applying the identical techniques used in the sprint to all comparison while keeping all other components unchanged. The result shows that the most of baseline method with different memory size benefited from the data augmentation. However, our method achieved the highest performance among all baseline, demonstrating that our self-paced sampling works effectively with the randomness introduced by the data augmentation. Our evaluation study examined two key components of Sprint, which are self-paced sampling for new task and it for the previous task. As shown in the table, Sprint achieves optimal performance when both components are present. Each component serves a distinct purpose. The former effectively mitigates the catastrophic forgetting as evidenced by lower forgetting score, while the latter enhances the learning of new tasks, leading to the improved loss accuracy score. Here, the loss forgetting is the average maximum forgetting of all tasks. And this demonstrates how these components work complementarily to enable a robust continual learning. Moving on to our visualization analysis, the figure shows TSNE visualization when we compare Sprint with the other top performing method, which are EWC, RWork, and RM, we can observe that the Sprint creates significantly reduced the overlap between the classes, demonstrating that our objective function promotes robust decision boundaries. A clear example of this improvement can be seen in the Sprint visualization, where the deep green and light green cluster are notably more distinct and compact compared to the counterparts in the RM visualization. In the RM, colored clusters exhibit considerable overlap and dispersion. Compared to EWC and RWork, our method Sprint reduced the overlap between the orange classes and the other classes. So let me conclude by summarizing our main contribution and feature directions. In this paper, we introduced a novel Sprint, a novel approach that bridges self-paced learning principles with continual learning. The key innovation of Sprint lies in its dynamic adaptation mechanism. It adjusts the complexity of samples based on the model's current learning capacity, handling both new and previous tasks effectively. And looking ahead, we see exciting opportunities to extend this work. Specifically, we plan to adapt our self-paced strategy to large foundation models. And our goal is to incorporate this approach in the distant metric function while maintaining the pre-trained representation of these powerful model processes. Thank you for listening.